Well, good evening, everyone. It is a pleasure to be back with you. I've seen some familiar faces and some new ones, and I'm very happy to be able to share with you the story of our solar system. Now, of course, can't possibly tell you the whole story in 1 hour, but we'll do with the best we can. And I always start this out by first describing why I chose that title. And it's partially because I'm not only going to just tell you a bunch of facts about the solar system. There will be some, of course. But I do want to build for you the story of the solar system, as Bill mentioned, starting out by trying to understand, well, how do we build this story? How do we understand what we know about the solar system? And then as we walk through this, you'll see me take an approach that's familiar to this audience. The approach how science works. We make observations. We build that into a theory. We test that theory. We improve that theory. So watch for that as we go along, and you'll see how we have, again, not only built up this story, but continue to enhance it today. So with that, let me kind of summarize the topics. I'm going to start with some basic properties of the solar system. Now, I know that this audience is well familiar with those basic properties, so I won't spend a lot of time on them. But I like to do that to build a foundation that we can then build further on, okay? Just to make sure we're all on the same page, so to speak. Then, as he mentioned, I will discuss our formation theory of the solar system. How did it get like it is today? How can we explain how it got like it is today? Then, in order to give us the best possible understanding of it, we're going to need to look beyond our solar system. Instead of just examining one, we'll look at the evidence from other solar systems. We can take that and build a broader, deeper picture of our own. And then we will finish up, of course, with some history of the solar system. How has it changed since its formation? So those are our main topics. Let's go ahead and get started. As I said, we'll start out with the basics here. You're all very familiar with the 5 major types of bodies in our solar system. There's the familiar terrestrial planets at the top: Mercury, Venus, Earth, and Mars. These are relatively smaller planets, rocky in composition, close to the sun. The Jovian planets are familiar, much larger, gaseous composition, farther from the sun. I'll touch briefly on the major moons of the solar system, and then the smaller bodies in the solar system that, again, I know you're familiar with: the asteroids, smaller rocky objects between Mars and Jupiter, and then comets and Kuiper Belt objects, smaller icy objects in the outer solar system. So that's where we begin, by just taking an overview of what we see in the solar system. And then we're going to look now at some of the properties of the solar system to answer these 2 main questions. How do the properties explain the formation and the history? Those are kind of our 2 main themes that you'll see us work through tonight. So let's get to it. We're all pretty familiar with the planets, large bodies moving around the sun. They all orbit in the same direction, in nearly the same plane. They also rotate in that same direction, with one exception. The moons of the solar system orbit their planets in the same direction and plane, at least the major moons, and they also rotate in that direction. So here, right off the start, we see some structure, we see some order, if you will. In other words, these major bodies, they're not just all flying around the solar system any direction they choose. There's some order. And that is giving us our first clue about how they formed. Okay? How about their location? Again, familiar. The rocky terrestrial planets, closer to the sun. Gaseous Jovian planets, farther from the sun. And of course, in recent years, we now have a 3rd category: icy dwarf planets. These are smaller objects, of course, much farther from the sun as well. Once again, we see a bit of order here, don't we? We don't see Jupiter orbiting where Venus is, and we don't see Mars orbiting where Neptune is. We see some patterns, some order. This is also a subtle clue for us that we can start to use as a basis for building our understanding. even the smaller bodies. Think of it. Those smaller asteroids are rocky in nature. They too are relatively closer to the sun. They're inside the orbit of Jupiter, of course. Whereas those icy comets and Kuiper Belt objects, they're farther from the sun. So we start to see these patterns. And we take that as our basis to move forward and build, again, an understanding on that. So let's do exactly that. We'll take these properties, simple as they may be, and start to explain its formation. And then, as I mentioned, we can continue to build on that as the presentation goes on, okay? The theory that scientists have developed, known as the Nebular Theory of Formation, basically states that our solar system formed from a giant cloud of gas and dust. See an example here to your upper right. And ultimately, this is how solar systems originate, as you can see in the lower right. So we know of numerous of these various clouds, but really the very first question we would need to address is, well, if there's this huge cloud of gas and dust out in space, where did it come from? Don't you think we got to back up a step? And the short answer is simply, the matter in this cloud came from previous generations of stars. As you know, stars go through a whole life cycle. In my previous lecture for you some time back, we went through that. And ultimately, nearly all stars in one manner or another, more gently or more violently, expel much of their matter out into space, don't they, at the end of their lives? Whether it's those low-mass stars that expel out planetary nebulae, or it's those high-mass stars that destroy themselves by ejecting a supernova remnant. So I like to say to my students sometimes, it's a little bit like nature recycles that material from a previous generation of stars, expands, cools, and very, very slowly, gravity, of course, then can work and to contract that matter into one of the clouds you see. Now, these clouds can be enormous. Okay, they can be light years across. They can have many thousands, even tens of thousands, the mass of our sun. So they're not just going to collapse down to one solar system. They're going to form numerous ones. And we'll see the kind of bit more detail in the steps to that. But for now, just think of these clouds slowly having that contraction, because in certain areas of the cloud, it can have a little higher density. A little higher density, a little lower density here. Here's where gravity can again do its work and contract those regions. Now, of course, as this occurs, the matter is going to be slightly denser. Gravity is going to again work to bring it more towards the center. And most of the matter is going to be formed in a central star like our sun at the very beginning of a new solar system. But part of our task tonight is to explain how that happens. You can again see this flattened disk here to the lower right. Yeah, you see a brighter, denser, more massive center to it, but you also see a flattened disk, don't you? And in that disk, you can see some concentrations, and I'm sure you can guess what those are going to turn into. So let's take now a few minutes, and we're going to walk through how the cloud contracts, how it forms this structure. Then we can build on that and go from there. As our cloud contracts, slowly but steadily, it's going to heat up. And we mentioned already that gravity is the driving force here. Why does the temperature increase? Some of you may be familiar with the concepts of potential energy. That simply means that you have this enormous structure. Many of the particles in this structure are farther from the center than others, and they have a greater distance, a potential distance, that they can fall towards the center under the influence of gravity. And you probably guessed that if gravity is a steady force on them, they're going to accelerate. They're going to speed up as they head towards the center. So one way we interpret the motion of these particles is to think of them speeding up as they're turning the potential energy into kinetic energy. And when we say kinetic energy, that's another way to describe thermal energy. The faster the particles move, the greater their thermal energy, and likewise then their temperature. Okay? As our cloud continues to contract, it's going to start to spin faster. Why would it do that? Well, here we have a principle known as the conservation of angular momentum. I often use for my students the example, maybe you saw this recently, during the Winter Olympics. We saw some of those wonderful athletes, those figure skaters. They go into their spin often with their arms extended, and what happens when they pull those arms in? Of course, they spin much faster, don't they? This is conservation of angular momentum. As the radius of an object shrinks, it still has that momentum in an angular motion that must be conserved, and therefore it must rotate faster. So that's what you can start to see here as we move from our first to our second image. The cloud is going to spin faster. Third step, as you see there, the cloud's going to flatten. Now, why would it flatten? Think of it this way. If you have this huge cloud spinning in the direction perpendicular to the spin axis, if I have a vertical spin axis here, in this direction, as the cloud begins to spin faster, there's going to be a net outward centrifugal force that's going to resist the contraction of the cloud in that direction preferentially. In contrast, material along the axis, vertically here in my example, feels no such centrifugal force. It's free to fall inwardly. This is why the cloud begins to flatten. And you can see that again in the third image. So here the laws of physics are essentially describing or kind of dictating what should happen to this cloud as gravity contracts it. This gives us something to work forward with. In other words, if we look out at some of those big clouds out in space, we see them, we would expect eventually to start to see this process. Now, make no mistake, this process takes a long time, okay? Hundreds of thousands of years, millions of years even. So we're not going to watch one cloud contract, but as you'll hear me describe in a few minutes, shouldn't we be able to look at multiple clouds and see them in various stages of this process? Yeah. So let's watch for that as we move forward, okay? So we've built an understanding of what we think should happen, how this should work, but you can see my question here. How can we confirm this? In science, of course, we always want evidence to establish and then confirm what we think should happen. And that's exactly what we're going to do now for a few minutes, is look at the evidence to confirm this picture, this nebular theory of formation. Well, we need go no further than a very familiar object to this audience. The famous Orion Nebula there you see. And some of you might remember that some years ago, the Hubble Space Telescope was turned towards it to look exactly for what we've described. Astronomers were very keen to find out, is this really what's happening in the Orion Nebula? For Hubble, we didn't quite have the telescope power and the resolution to see what we were looking for, but notice not only in the left image, but some close-ups on the right. Sure enough, we saw disks of material around young stars. As you can see, we now call these proplids, or acronym for protoplanetary disks. It's exactly what they appear. And as you can see, they don't all look identical, of course, because they're all at various stages of their development. Some are a little farther along, some are just getting started. And we see some very interesting structure, of course, that adds detail to our big picture. But there they are. There they are. Just as we expected from what we just described. Okay, well, after Hubble's initial images, we went back some years later using the Atacama Large Millimeter Array, or ALMA. And boy, look at the images there. Isn't that spectacular to see these protoplanetary disks? You might know that ALMA looks at different wavelengths than Hubble. But my goodness, look at the resolution here. We not only see disks, but we start to see structure in the disks. Rings of material interspersed with gaps in the disk? Well, as we're about to discover, as we're about to see here in just a minute, this is also a prediction of our theory. This is also a sign of planetary formation in the disks. And again, they certainly don't all look identical. Not only are they different in mass and size, but in age. Some have developed a little farther along. Some are just starting out. So let's take a closer look at some of that and see what we can learn. Here on the right, you see some close-ups of a couple of them, the H.L. Tauri disk and the G.W. Orionis disk. Notice again the gaps. What's happening there? Here's where planets are forming. They're essentially gathering material together as they begin to form, and so material is gradually drawn together and becomes much less dense in these gaps, leaving areas where the material is still relatively denser, more plentiful, and so we see a ring. So this is another prediction of our theory that we should expect to see, and we do see, now that we have the increased resolution of ALMA to show us these. So again, as you know, this is how science progresses. We build an initial theory, we look for further evidence to support it, and that makes our theory better, helps us to enlarge, increase, deepen our understanding. Let me go ahead and start this little animation just to give you an example of that. Watch closely, and over time you'll see the disc start out relatively smoothly, but sure enough, notice how the gaps in the disc grow. It leaves the appearance then of these rings of material where their matter is still fairly dense. Okay? So this gives us another step, so to speak, in our description, our understanding of what's happening in these disks. But you can see my next question there. So, okay, as this happens, what about the temperature of the disk? Well, at first it's fairly obvious that surely the closer you are to a star, the warmer it's going to be, no question about that. So we would expect a range of temperatures in the disk, warmer and closer towards the center and colder the farther out you go. In fact, we can again model what we would expect to see in terms of the change in temperature with this graph. Here you see the distance from the center on the horizontal axis, temperature on the vertical. We've got a little image at the top kind of illustrating what we're going to describe. Clearly, you can see the graph shows a higher temperature closer to the center. It can reach even several thousand degrees as you get right up towards that young star. But you can also see, of course, the temperature is steadily decreasing, dramatically at first, more gradually later. But I want to make a few points here. Notice a couple of temperatures are pointed out for us. Let's start way over on the left there. If you can see, it says it's about 1,300 degrees. It's pretty hot, isn't it? If you look really closely at that little image at top, you see over to the left something called the rock-metal condensation line. Here is a distance from the star at which it is so hot that not even rock and metal will condense into a solid. So as we'll talk about in just a minute, we really wouldn't expect planets to form there if you can't even have solid matter. Go out a little bit further, and you can see what's called now the frost line. Sometimes I've heard it called the snow line or the ice line, but here is a distance at which, inside of that distance, rock and metal can solidify. The temperature is such that you can get solid material, but not ice or gas. Those are what we call lighter volatile elements. You probably heard that term. They cannot solidify there as the temperature still is relatively high. But as you can clearly see, at about roughly 3.5 astronomical units, outside the frost line, the temperature is low enough for gas and ice to condense. So we can now have bodies building. So clearly temperature plays an important role here, doesn't it? We would not expect planets extremely close to a young star. All the material is vaporized. Farther out, we would expect bodies to form of rock and metal. And at a certain distance, even now gas and ice can condense into a solid form. This is what we would expect to see in those disks of material. Here's just a little different view of that. Once again, for a star like our sun, roughly speaking, inside of about 0.3 AU, it's too hot even for rock and metal. From that distance out to that frost line, roughly 3.5 AU. Then after that point, we can build planets not only of rock and metal, but of ice as well. So again, this is the prediction of what we understand should be happening there. And astronomers have carried this forward and has proved to be a sound model, as we're going to continue to see. So the frost line is a key delimiter, if you will, for the composition of planets in our solar system. All right, so we've established what should happen and where, but how do planets form? Let's dive into that. Start out with the term for this process called accretion. I'm going to pause my video just for a second here if I can. There we go. Maybe you've heard that term, accretion. What does that mean? Accretion basically means, if I can get my slide to advance, come on. I think I broke it. The smallest molecules will begin to stick together into tiny particles. Those tiny particles will begin to stick together into larger objects we call planetesimals. They're nowhere near as big as a real planet, but they're starting to grow into objects tens of feet, hundreds of feet, sometimes even thousands of feet across. Planetesimals, remember that term. And at some point, of course, those planetesimals now are getting big enough. They have just a little bit of gravity to tug on each other. Many of them are going to collide, stick together, and eventually form planets. You can see the three major stages down there at the lower right. Start out with countless small particles building into more planetesimals there in the center. And those collide and stick together to form our larger planets in the right-hand example. And you see a graphic there to the upper left as well, showing the later stages of a planet with its gravity now able to literally pull in more planetesimals to add to its mass. Okay, so let's go back to my animation there that I let run after all. It's okay. Let's just watch closely here. Our disk is going to be obviously spinning and flattened. Notice the gaps and the rings. What we should see in the gaps is little planets forming. And I'll point them out to you. You can see one up at about, roughly the 2 o'clock position and maybe the 9 o'clock position. You see those little white objects forming there? Got another one at about 4 o'clock inside the second ring. And notice too, of course, as the planets again grow in size and they're gathering material in, notice how the disk is changing. More and more of the matter is being incorporated into building those planets. And ultimately, as our young star begins to grow, heat up, and give off more energy, it's going to start to sweep some of that material free. And notice now how our planets have grown larger. Our disk has, I guess you could say, dissipated somewhat. Okay? And we're going to end up with a solar system very much that you and I are familiar with. I'll let that run one more time if you want to have one last look at it. So accretion is the process by which planets are built. Fairly simple, fairly straightforward, that smaller objects stick together, they grow into planetesimals, those bodies merge together into larger planets. Let's see if we can go forward. There we go. Let's take a minute and talk about the large moons in our solar system. How'd they form? Simply put, in a very similar manner to what we've already described, but not on quite so large of a scale. In other words, picture now the very young but very large Jovian planets, Jupiter and Saturn especially. They've got so much matter, they're going to form an enormous disk around themselves. You probably know that Jupiter has several hundred times the mass of the Earth. Saturn has almost 100 times the mass. So that's a pretty large amount of material, that disk is also going to contract, heat up in the center, spin faster, and flatten. And particles in that disk are going to stick together in accretion. They're going to grow larger, and they're going to end up as larger moons. Okay? So again, a pretty similar process, if you will. You see there in the bottom image the 4 large moons of Jupiter at top. At lower left is Saturn's large moons, Uranus in bottom center, and Neptune's large moon to the lower right. You might be thinking, well, wait a minute, there is one large moon missing, isn't there? Recognize that one? Our moon is similar in size to those. It's a large moon. Is that how our moon formed? Well, let's step back a minute and think for a minute. Mercury, Venus, and Mars, the other terrestrial worlds, do not have a large moon, do they? So it would not be wrong to say, well, wait a minute, Earth's large moon seems to be an exception among the terrestrial planets, wouldn't it? The Jovian planets all seem to have large moons, but only Earth has a large moon. How did it form? It is an exception. We now think it was due to an enormous impact to the early Earth by a very large body, technically a planetary-sized body. Maybe you've heard this term Theia. Have you heard that name? So if you want to go look that up, learn more about why we think our moon formed that way. We actually had some recent research just released. Why would a large planetary body strike the Earth? How would that play out? You know, at first we think of collisions, we think, wow, they're going to get smashed apart, right? But stop and think about this. As our young Earth and the other planets are now orbiting the sun, any objects near them are going to orbit at approximately the same speed, aren't they? Some of you are familiar with the orbital laws of Johannes Kepler and so on. At a certain distance from the sun, you orbit at a certain speed. So in other words, bodies at the relatively same distance are going to orbit at relatively the same velocity. So in other words, many of these collisions would not have been catastrophic. These bodies, sure, would have smashed together. There would have been a lot of debris, but that debris would not have such a large velocity that most of it was lost. Instead, our current models show that the material, nearly all of it, would have remained with the early Earth and reaccreted into our large moon. So that's another story. Maybe we can get to that later if you like. But it explains the large moons of our solar system. And by the way, you can see here how sometimes, again, our theory may not necessarily describe an exception to a rule, but often, if not usually, we can say, well, wait a minute, here's maybe what happened in that case. We can add to the theory, can't we? Okay. How about the smaller bodies in the solar system? Over on the left is a close-up image of a large asteroid, and at top right, obviously some images of cometary nuclei. Well, it's very accurate to say these can well be considered as leftover planetesimals that never accreted into a planet for several reasons. And our asteroids, of course, primarily made of rock, they're in the inner solar system. That makes sense, doesn't it? We would almost expect that any remaining planetesimals relatively near the sun would have to be made of rock, wouldn't they? We wouldn't expect many icy ones there, simply too warm. But farther out, sure, beyond the frost line, there could be many, many icy planetesimals that were never drawn into a planet. In fact, think about this. I'll come back to this. The farther out we move from the center of the solar system, obviously the volume of space is increasing not only steadily, but exponentially. Okay? And that means that the farther you are from the center, the number of these planetesimals would increase not just steadily, but exponentially. In other words, there would be a lot more material farther out in the solar system in the form of planetesimals, and ultimately, obviously, in the form of those huge planets. So again, you can see how our theory continues to explain We can continue to dig deeper, learn more, add to that theory, and improve it as time goes on. Well, here's our next big question. Okay, sounds good. When did this happen? Well, to know the age of the solar system, one of the fundamental primary ways is to find the age of the planets. How do you find the age of the planets? You got to find the age of the material they're made out of, the rocks, essentially. So I'm going to describe this process you see here in the graph and see how that can help us to come to an understanding of the age of the planets, Earth included. Earth, obviously, the one that we can get our hands on any rocks we want, right? But we have been able to obtain rocks elsewhere from the solar system. So let me come back to that in just a minute. All right, in our graph here, you see the illustration of how some elements will gradually but steadily change into other elements. Okay, and this is known as radiometric dating. I'll start with a very simple example. We'll build on that a little bit, but let's pretend we somehow found some rock made out of potassium-40. Well, if you look at our graph, after 1.25 billion years, you see on the graph right about there, half of the potassium-40 has now changed into argon-40. So again, grossly oversimplifying, if you had a rock that was half potassium, half argon, you could probably conclude safely that it was about 1.25 billion years old. See where we're going there? How about we wait another 1.25 billion years? 2 half-lives of the potassium. Well, 1/2 of the remaining half has changed, and now our proportions are going to be, 25% potassium, 75% argon. And likewise, after 3 half-lives, we're down to 12.5% potassium, 87.5% argon. So obviously, it's not quite so simple in daily life, but by now, geologists can take a rock, look not only for these 2 elements, but others, and use these decay rates to determine how old the rock is. Well, obviously, the oldest rocks we could find would give us a pretty good idea of the age of the planet, don't you think? So what do we find? We find that Earth rocks are at least 3.8 billion years old. In recent years, there's been a few that might even be a bit older than that. But years ago, when our Apollo astronauts went to the moon, they brought back some moon rocks that were dated at almost 4.4 billion years. In fact, there's a little video clip somewhere if you want to go look for this. I'll never forget seeing it a few times where one of the astronauts, they were highly trained before they left, of course. Now, we want you to look for these rocks and pick up samples and look for that. So he's out and he's looking for rocks and things. And he looked over and he said, "I think I found what we came for." And of course, back on Earth, they're like, what are you seeing? "Well, I'm seeing such and such a rock, blah, blah, blah." Pick it up. Bring it home. And when they got back to Earth, they named it the Genesis rock. If you want to look that up, because it was extremely old, not quite 4.4 billion years old. Okay, so kind of an interesting story. And don't forget that once in a while we get free rocks from space, don't we? Meteorites. We pick those up and date those, and some of those have been dated close to 4.5 billion years old. So if we had just a bit more time for these rocks to have condensed early in the solar system, we come to this number. About 4.57 billion years for the age of our solar system. That's kind of a profound number, isn't it, to know when the solar system began? I think that's pretty amazing. We have other evidence from stellar astronomy. We can make a pretty good educated guess on how old the sun would be. But here's solid evidence we can get our hands on and confirm this number. By the way, in astronomy, we throw about billions of this and billions of that, don't we? How much is a billion? It's a lot. A billion's 1,000 million. So sometimes I'll tell my students, maybe it helps you kind of grasp this if you think of it as 4,570 million years old. I don't know, maybe that helps you, maybe not, but a million years is a long time to me, and 4,570 million years old. So we've learned a great deal, haven't we? But as promised earlier, now we want to look at some other solar systems. Because let's face it, we've only talked about one so far. And sometimes I'll use this with my students. I'll say, you know, if you wanted to study human beings, sure, you could pick one human and study that human, their life and their experience, but you just have one human, don't you? Instead, of course, sociologists and others, they'll study hundreds, thousands of humans, whole populations, to give such a bigger picture, such a bigger context, doesn't it? Such tremendous variety. It's the same way with solar systems. Back in the mid-1990s, some of you remember when we first gained the ability to begin studying actual solar systems. We suspected pretty strongly they were there. We had some tantalizing hints. But do some of you remember the first extrasolar planets discovered? Yeah, that was a time you wouldn't forget. That was an amazing time. So let's take a look just briefly at what we found, but more importantly, what does that mean for our solar system? What context does it put our solar system into? Okay? Here's a simple diagram I like to use showing our solar system at top and a number of other ones there. Notice Mercury, Venus, Earth, and Mars, the inner terrestrial worlds, certain distances from our sun. But notice the other solar systems. There's some large Jovian planets closer to their sun than our terrestrial planets? Well, wait a minute. This is evidence of some dramatic differences, isn't it? So does that mean that what I described to you is inaccurate? No. Our nebular theory is solid. It is well supported. It is well accepted. Terrestrial planets form here. Jovian planets form there. And yet there they are. Okay, there they are. Jovian planets inside the frost line of their star. How can that be? Well, at this point in time, scientists discussed this, to put it mildly, argued about it, and came up with the idea that, yeah, it's true that those planets could not form there. Well, if they couldn't form there, how'd they get there? There had to be dramatic changes in these solar systems. There's a saying, I don't know if I always get it right, but it's something like, you know, once you eliminate the impossible, what remains must have been what happened. So we take that and we say, well, if they didn't form there, they had to move there. Today they're known as hot Jupiters. Have you heard that term, I think? In other words, Jovian planets that formed outside their star's frost line moved inwardly. That was a big surprise because we all tended to assume that planets formed as I described them and they pretty much stayed in their orbits, right? Maybe not. And so years ago, found evidence that no, they don't always just stay in their orbits. So this led us to understand planetary orbits can and do change. And well, that opened up a whole new way to study solar systems, didn't it? You now picture that various solar systems would go through different stages of development. Ours is at a certain stage. But let's go on and press on and learn a little bit more about this. If these planets change their orbits, how do you move a planet? I mean, they're nowhere near as big as stars, but planets can be pretty massive, right? Think of Jupiter. How do you move a Jupiter planet? Well, you probably know the force of gravity is the answer to that. So let's play this out for a minute. You see here again a early young solar system. They're not usually green, but we'll take the artist's impression there. And you can picture, we'll just start out with one planet, accreting material, growing, pulling matter in, and basically clearing out the gap in the disk. Now, I want you to think about this for a minute. Look at the amount of matter outside the gap compared to the matter inside the gap. clearly it sure looks like a lot more material, doesn't it? And you'd be right. In fact, inside the gap, you're going to have mostly, rocky metal, dust kind of material. Outside, you're going to have some rock and metal and dust, but you're also going to have a lot of gas and ice. So in other words, there is a lot more mass outside that planet's orbit than inside. What's that going to do to the planet? Well, surely that mass outside has a greater gravitational pull on that planet than the mass inside. Okay, what does that mean? Think now of the planet in its orbit. We could use the term it has a certain orbital energy, that momentum. And as that matter outside tugs on that planet, it's going to lose some of that orbital energy. It's going to migrate inwardly. This is how you move a planet. Generally, this is going to happen relatively early in the history of a solar system. A little more rigorous way to describe that would be that it reduces the angular momentum, but you get the picture. This is how we envision planets migrating inwardly from their original orbit where they formed. Okay? It's a very good way, I guess, to explain how that could happen. Let's take a second possible explanation, gravitational encounters. Now we'll add a few more planets. Look at our solar system. We don't just have one planet, do we? Now planets in their orbits, from time to time, certainly are not orbiting in a perfect circle. They're in slightly elliptical orbits. They may get a little closer to each other from time to time. And as they do that, their gravitational effect on each other begins to have a change in their orbits. Sometimes they may get quite close to each other, and there would be a dramatic change in their orbits. One's going to gain angular momentum, one's going to lose some, and fall inwardly. Okay? In fact, in some cases, we think, certainly is very possible, if you had two planets approach each other closely, one could gain enough angular momentum to literally be ejected out of the planetary system while the other fell inward dramatically. So this is a second recognized mechanism on how planets change their orbits. There's other methods, but they get rather complex, so we're just going to stick with these two for tonight. And again, it's a nice way to illustrate how we now have a increased understanding of solar systems because we looked out and are now able to study other solar systems. This isn't very obvious in our solar system, or is it? Let me come back to that in just a minute too, okay? Even the small bodies in solar systems, asteroids and comets, they can play a role here too. Now you say, well, wait a minute, a little asteroid's not going to, affect Jupiter's orbit, is it? Well, technically speaking, it's going to affect it just very little, isn't it? In fact, the little asteroid is going to pay a price, isn't it? Jupiter's gravity on that asteroid may well send it flung outward or inward. But go back for a minute to what we described about that early planetary disks. There are uncounted, probably billions of these small planetesimals floating around, okay? And their effect adds up. So yes, the planetary disk, these planetesimals, can, in fact, have a significant effect on the orbits of planets. So once again, when we start to broaden our understanding and take this into account, you can see my comment here that our nebular theory is improved. It explains more. Yeah, we started with a very simple first picture, but we've built it, haven't we? We've improved it, we've expanded it to explain more. That's the sign of a good theory. That whenever new discoveries are made, we can incorporate them and improve the theory. It gets bigger, it gets better, more accurate even. Okay, well, I've kind of hinted at this question. That's pretty interesting to see these other solar systems, all at different stages, showing evidence of dramatic changes. What about ours? Could this have happened to our solar system? Let's talk about this. Here I'm going to show you some hypothetical possible models for planetary migration. Start at the top of me, above the A there section. Notice how the planets, we think, formed relatively closer to each other than we see them today. There's your terrestrial planets to the left. There's what today we would call the asteroid belt. In other words, all those planetesimals. Then you see big Jupiter and Saturn, Neptune and Uranus, and a lot of planetesimals in the outer solar system. Okay, what's going to happen? Well, remember I've described how large planets like Jupiter and Saturn could clear a gap in the disk. And once they do that, the material outside the gap has a greater gravitational pull than the material inside. Jupiter and Saturn migrate inward. Notice that in the second frame there? Notice Jupiter and Saturn moving inward. Well, they plow right into that rich region of planetesimals. And they begin to scatter these violently. So this was a very busy time, if you will, in the solar system's early history as these massive Jovian planets scatter a lot of these planetesimals, okay? Of course, the planetesimals pay the price. They get flung outwardly or inwardly, okay? Oh, and by the way, let me make one quick comment here you see in parentheses before we move on. This also would significantly reduce the number of those planetesimals in the region inside of Jupiter. And that, we think, can also help us explain something that's come to be known as the small Mars problem. Have you heard that before? What's the small Mars problem? Well, have you ever wondered why Mars is smaller than the Earth? Or Venus? Mercury's smaller, but it's awfully close to the sun, and surely there was less material to build Mercury that close to the sun. But what about Mars? Mars is only about 10% the mass of the Earth. If indeed this scenario is correct, as Jupiter scattered that early planetesimal disk of material outward, much less matter was available for Mars to accrete, for Mars to grow. Once again, another fact that may well explain what happened to Mars. It improves our theory. It expands its reach. It helps us understand more about the early solar system. Okay, well, let's go to frame C here now. As Saturn gets close to Jupiter, they develop what's known as an orbital resonance. Maybe you've heard this term. This means that as Saturn orbited the Sun once, Jupiter and Saturn moved into position where Jupiter would orbit twice. What does that do? Well, that means every time Jupiter and Saturn line up, they give each other a pretty good tug. They begin to affect each other's orbits on a regular basis, not just a random basis. This has the effect of moving them back outward, farther from the early sun. Well, as they do that, there's more planetesimals farther out, isn't there, in that disk? Their powerful gravity begins to affect those. Countless ones of those are thrown out of the solar system or inwardly towards the sun. In fact, this could also likely help us explain what we today call the Oort cloud. Have you heard that term? Far out from the sun, many thousands of astronomical units, we envision a spherical cloud of small icy planetesimals. This may well have played a major role in helping to form that. At this point, the solar system starts to look a lot more like it does today, as you see in the bottom frame there. We come along, we look at it, and we say, oh, that's very interesting, look at our solar system, it's very nice, but little did we know that perhaps it's been through some dramatic changes, hasn't it? So these are likely scenarios, but once again, is there any evidence? Is there support for this? Can we find any remaining evidence? Let's talk about that. Some years ago, astronomers developed what's known as the Grand TAC model. And if you're interested at all, you can see a reference to the lower right there of a professional paper you might go look up by Walsh and Batigan and Laughlin that brought this forward. And they took what I just described and established it and refined it and improved it far beyond what I could describe here. It envisions Jupiter forming at about 3.5 times the Earth's distance from the Sun, astronomical units, but then they migrated inwardly to about 1.5 AU. If you know, that's the current distance of Mars. So yeah, they got significantly closer, didn't they? Okay, but then remember I explained how then they would move back outwardly once they entered into this resonance. Okay, and Jupiter would have ended up at about 5 AU, Saturn at about not quite 10. Okay, so then in other words, what they're doing is they're quantifying what I described. I gave you just the first picture, but now they're going to put some numbers to it and do some calculations. Say, could this really have happened? Well, again, this would have disrupted the inner disk, limiting the material to form Mars, and it also would have disrupted that outer disk of material. And the solar system as a whole now has significantly fewer planetesimals both inside and outside Jupiter's orbit. It's almost like it's cleared out even more room in our solar system. You see in parentheses I left myself another reminder there. This even explains yet another interesting fact about our solar system. I'll come back to this in a minute. The possible origin of some of the largest asteroids. You might know the object we used to think was an asteroid, Ceres. Let me come back to that in just a minute here and see how that is part of this bigger picture. So the Grand TAC model has been examined. Many planetary astronomers feel confident this may well likely have happened. The second model, called the Nice model for the city over in France where it was developed, talks about how the solar system also likely was restructured, possibly later than the Grand TAC model. We're going to look at these first three frames down at the bottom here. Over to the lower left, you can see what we're trying to show is the orbits of Jupiter, Saturn, Neptune, and Uranus. And by the way, I did not get those in the wrong order. We think when the solar system formed that Neptune and Uranus had different orbits. So I'll explain that. You also notice that it certainly appears that they formed pretty close together, and we think that was true too. In fact, there's evidence that says that possibly there could have been a fifth Jovian planet in our solar system at the beginning. That obviously is no longer there. So let me play this out for you a little bit here. We start off there in that first frame. Again, we talked about how orbital eccentricities would cause Jupiter and Saturn to move inwardly, scattering planetesimals, many of which may likely also have contributed to building what we today call the Kuiper belt of objects, right? Okay? Now notice in that middle frame, if you look really closely, that blue orbit there doesn't look so centered on the sun anymore, does it? This is where we described earlier this idea of planetary interaction, so to speak. Two planets pulling on each other, disrupting their orbits. This would have stirred up the solar system dramatically, okay? The planetesimals were stirred up. Their gravity affected the planets. Clearly, the planets' gravity affected theirs. This could have well initiated the swap of Neptune and Uranus orbits. How about that? That's quite a thought, isn't it? And ultimately, in our right-hand frame there, you can see the solar system looks a lot clearer, doesn't it? Far fewer planetesimals. So some dramatic changes are put forward in this model as well. In fact, again, I keep saying that the migrating of all these planetesimals likely contributed to the formation of the Kuiper belt, the Oort cloud, as we see them today. And I left myself one more note there. What's the LHB? So just briefly, the LHB is an acronym for the Late Heavy Bombardment. What is that? So planetary scientists found some interesting facts some years ago. When we look at the surface of our moon, Mercury, Mars to a lesser degree, and even a little bit on the Jovian moons, we can get a pretty good estimate of when various impacts happened. Well, this one happened this long ago, and that long ago, and that long ago, based on various factors, their sizes, how well preserved they are, so forth. And a startling conclusion was reached. It appears from those impact patterns on all these bodies that after the initial formation of the solar system, perhaps 500 million years afterwards, there was an intense burst of cratering on these bodies. In other words, we just see craters like, wow, look at all these craters that are of this age. You follow me? Perhaps what we're seeing is evidence of this dramatic scattering of all these planetesimals. Scientists think that's a very possible scenario. All right, I promised you this animation. Let's have a look here at our solar system as the millions of years are ticking off the top there. I'm going to try to stop it just at the right moment to show you what's going to happen as we get to not quite 800 million years after formation. Here you see the orbits of, again, Jupiter, Saturn, Neptune, and Uranus. And then our outer planetesimal disk still in place, very well populated, isn't it? Let me go forward carefully, see if I can do this slowly, because things happen very quickly. Okay, I'll just try to get us up there, 600, 700, oops, see, I always tend to mess it up. I stopped it, let's go up like this. Go up there and we'll do it like this, ready? What I'm gonna try to do is stop it right before these dramatic changes occur, ready? Let's see if I can do it here. 800 up. I always goof this up, I tell you. Try it one more time, sorry. What happens is the kind of times out. All right, ready? Here we go. Look how quickly things can change. Not only do you, of course, see the tremendous scattering of all those planetesimals, but notice the orbits. Let me see if I can just click ahead just a bit. And watch closely again the orbits of Uranus and Neptune. Swap. Now Neptune in blue is the outer planet. Look at the orbit of Uranus. It's not centered on the sun, isn't it? It's very elliptical. So in other words, this is a time of great change in the solar system. Okay? So what a dramatic evidence we have of, again, likely change in our solar system that we maybe never expect. I'll try one more time here. Ready? There you go. Look at that. Jupiter shifts Saturn outward. Their influence helps to disrupt the orbits of Neptune and Uranus. As they swap orbits, you're going to greatly scatter those planetesimals, losing much of that, likely contributing to that late heavy bombardment. Well, are you looking at the solar system a little differently by now? Promise you I'd come back to Ceres. Long ago, some of us, well, all of us thought, well, Ceres is like the largest asteroid. Remember that many years ago? We know it's not an asteroid anymore. In fact, it's one of the few objects we now call a, anybody? Dwarf planet, thank you. NASA sent the Dawn mission to go visit Ceres. We suspected what we would find, and sure enough, we found that it has a very high composition, including ice. Possibly even some subsurface water. We don't know that for sure, but there's a picture of it. It's large enough to have formed itself into a nice spherical shape, unlike the asteroids. But the point is, if it's more than half ice, could it have formed inside the frost line? No, we established that long ago, didn't we? So now we think it very likely that Ceres probably formed in the outer solar system, where there was ice. During all this chaos, at some point in the solar system history, it migrated inwardly. Kind of interesting to think of that, isn't it? In other words, it's not so much different from Pluto. And yet here it is in the inner solar system. Okay, so kind of an interesting additional fact that what we just saw helps explain this as well. Okay? Well, as I said, we certainly look very differently at the solar system now, don't we? And I hope I painted for you the story of the solar system, how it formed, how it developed, how it changed. Okay, there's solid evidence for the things I've described here tonight. It's a fascinating field to go off and try to keep up with some of those things. You know that there's been some interesting other comments made. For example, some have thought maybe there is still a large Jovian planet out there somewhere. Maybe. We don't know. But this theory certainly allows for that. Okay? And we've been looking for that. You've heard them talk about Planet 9 again. So that's part of this story of the solar system. So at this point, where do we go from here? I think I've made clear that our knowledge continues to expand, to increase, to deepen, become clearer. And I like to say that when we learn about different parts of the solar system, well, it expands our knowledge of the whole solar system, doesn't it? In other words, you saw me weave in there certain kind of side stories, this late heavy bombardment, the swapping of the orbits of Uranus and Neptune. Sure, those are interesting in their own, but they explain so much more, don't they? And where did much of this begin? It began with us looking at other solar systems. My goodness, how much work there is to be done to try to understand them, see how maybe they've changed. So you can bet planetary scientists are hard at work doing just that. So my advice to you, as we used to say, is watch for the next exciting developments in the story of our solar system. Thanks for having me tonight. It's great to be with you. Hope you've saved up a few questions for me. Before we open the floor for that, let me just make a couple of other comments. I think you all know that I've gotten quite a number of these presentations out on YouTube. So please go ahead and just type my name in and search for some of those. I think I shared with you the stars of birth, life, and death in recent years. You can see some other ones there. Relativity. Okay. I did one on our Earth. After all the years I've talked about the universe, I said, you know, I think it's time to do Earth. So check that one out if you like. For those that might be interested, I also have 2 short courses in astronomy online there. You can just go watch these videos. They're a little bit shorter, okay, than the full lectures. One on our solar system, one on stars and galaxies, so you might enjoy those, okay? And when I gave this lecture recently at the college, I thought I would ask the audience if they might be interested in our next one. How about that? Is it about time for that? We've all been waiting, haven't we? And we hope very soon now this will become a reality, that we will finally return to the moon. All right, well now it's your turn to fire away. I think we might have microphones, so we'll open the floor and be glad to answer any of your questions.
So, what's the say regarding Uranus? Because its axis spins regular solar system. Some people have said, how do you think about it? You know, it's a gyroscope. If you try to flip the gyroscope 90 degrees, and then all the planets and rings, it's also, so it doesn't fit this, right? So what's the latest spin in that?
So you make some good points. If you could hear him, he basically said, so Uranus is tipped over on its orbit, roughly 98 degrees, I think. And you made a good point. He said, so are the orbits of its satellites. So if you just smack into Uranus and tip it over, it's some large object, well, what about all the satellites? So good point. There is more to it than our simple analogies. Since the satellites are orbiting also like that, that would tell us that Uranus would have had to be flipped before those satellites formed, wouldn't it? That would at least be possible. And by the way, when might that have happened? I mean, how do you smack into Uranus and tip it over? It would have to be early in the solar system when there were still a lot more of these planetesimals, especially a pretty large one. You're right about this idea about, oh, like a gyroscope, it's hard to tip over, isn't it? It has its own stability, I'll just say it like that. So, to my knowledge, this is by no means something that we've solved. There are some good ideas, there are some good ways to explain it. I don't have all the details for you, but it's a good example of what I kept doing up here. We see something, we want to understand it, we try to explain it. Sometimes it takes a while to put together something that's plausible. Often that kind of thing is done by modeling it. Let's try this idea and see what that play. Oh, look at it, did that. Well, that's not really what we thought, but let's try another model. And it does take some time. Okay, it's called a Monte Carlo approach to things. And sooner or later, we tend to constrain it and say, well, it can't be all this, so it's probably somewhere kind of in this what we call parameter space. And let's adjust that knob a little bit and tweak that. Oh, we're getting a little closer. We gradually work this. So, good question. Now you got me wanting to go home and check it out, see what is the very latest. But to this point, it's true. We think a large impact caused that. But very good point about the moons. This would have happened pretty early. Yeah, good question. Okay. One over here or one here? Sure, go ahead. You go ahead.
Yeah, my name is Stefan Sharmani, from here. So these days I'm going from church to church, explaining them the human beings and our relationship with each other. And I tell them we are very small family compared to the entire universe. So how do we explain the size of the Earth compared to the universe to a layman in a very simple way?
Explain it to a
The size of our
size.
Earth compared to the universe. How do you explain it?
Well, I suppose you could take a
Very
ratio.
simple way.
Yeah, if I understood you right, I suppose you could take a ratio like the Earth is this many miles in diameter. How many miles in diameter is the universe? We usually use light years, don't we? Well, it's about 5.8 trillion miles in a light year. So you do the math if you want. Say, well, the universe is this many miles across. I think what did I come up with sometime? I had my students do it once. I forget the exact number. And I don't remember the exact results, but it came out to, well, the Earth compared to the size of the universe is like the Earth compared to the size of an atom or something like that. I forgot. It's an enormous amount, orders of magnitude. Might have been much smaller than that even. So yeah, we are a speck on a speck in a speck, our Milky Way. And I don't know how big that is, but so yeah, it's very, very large. Yeah. Is there a hand over here, I thought? Yes, sir?
Yeah, in your slide where you showed the coagulation of fragments and all of a sudden everything got dispersed and they changed orbits.
Yeah.
Any idea what caused that?
Yeah, that particular animation only showed more of a relative model. It wasn't terribly precise, but you get the idea. If I go back here, maybe I skipped over that quickly, but some of my comments had to do with as Jupiter and Saturn moved outward, okay? Remember we said that first they migrate in, then they migrate out. As they move outward, they would have disrupted at least the orbit of Neptune, which was then next one out. If you disturb Neptune, it moves out into an orbit where it can now disturb Uranus. And this is what's intriguing about that model is simply that from a very small initial disturbance, you suddenly get a larger disturbance. I forget the exact terminology for it, but yeah, there is a precedent for that in nature that sometimes, I think the extreme one, you ever hear about the butterfly effect? They claim, oh, there's a little butterfly and then this happens and then happens that. So a small initial disturbance set that all off. Yeah, can you imagine? Wasn't a butterfly, but. Okay, back over here.
Wasn't sure that the switch was on. When we first started detecting exoplanets, this hot Jupiter problem and massive, apparently massive planetary bodies near their relative stars, people were attributing that to the mechanisms we were using for detecting them. That by looking at gravitational wobbles and so on and so forth, we were giving precedence to more massive objects. And over time, that has begun to settle out, and we've begun to identify larger and larger varieties of objects as exoplanets. But as I understand it now, something in the Uranus or Neptune size seems to be the average overall of what we're seeing. Is that still mostly attributable to our weaknesses in our ability to detect things smaller, or do we feel like that reflects some fundamental characteristics?
That's a long question. So part of all of that, what you described, yes, as time has gone on, we've gotten better at examining these planets. You're right. Initially, they had what we call kind of observational noise. Well, wait a minute, how accurate are your measurements, all that kind of thing. But that gradually worked its way out. Yes, it's become that Uranus, Neptune-sized planets seem very common, very popular in solar systems, if you will. And we don't know the exact reason, but it just seems to be a size nature favors. We've also discovered such a richness that we never suspected in recent years. Maybe you've heard the term super Earths. Have you heard that? So you can build a terrestrial planet bigger than Earth, but as you start to get it a little bigger, a little bigger, a little bigger, well, is there some boundary between that and a Jovian planet? See? And there's not a black and white line, because the larger you make a terrestrial world, the more likely it is to hold on to more gas in its atmosphere. And as you build a bigger atmosphere, does this planet now start to look more like a Neptune? Yeah, and likewise with that. If you start out with a Neptune planet and it wanders in closer to its star and starts to lose some of its gas, what do you end up with? So again, a great richness. Yes, we found lots of those. That's one reason why some scientists have really pushed, could we please send a spacecraft back to Uranus and Neptune? But we haven't been there in, what, 40 years or something, right? So yeah, great richness in planets. Our solar system's one of surely billions. And it's one. And we understand it pretty darn well, how it's formed, but my goodness, can you imagine the rich stories to be told out there, yeah. Okay? Here? And then over there?
Having said that, with the planetary alignment, that must have some effect on the orbit of the planet.
Planetary alignment? What do you mean by that?
Well, we had the planets all lined up
Oh,
in a row.
okay.
And they making any effort to measure any discrepancy from current planets to what effect that might have?
Okay, so first of all, when we see, like you describe a planetary alignment, that's primarily a perspective effect. Here, we're on Earth, we happen to look out, we do see them lined up, you're right, periodically. They're still in their well-known orbits. There's no significant changes that we've detected over many decades. And by the way, I wanted to reassure you, all those changes you saw, those are in the past. So we don't anticipate any such thing. We've measured their orbits to fractions of a second, and they seem to be very stable. That does not rule out future changes, but nothing is on the radar. Yeah, so you can sleep well at night, okay? Yeah, right.
Regarding the age of the Earth, is there any other methods other than looking at rocks? Because with the tectonic activity, the oldest rocks probably don't even exist anymore.
You're exactly right. The oldest rocks on Earth do not, or that were on Earth, do not exist anymore. Why not? I always make my students answer that one too. I heard somebody.
They decay.
They decay. They change. Erosion, right? Volcanism melts them. Okay. Even tectonics crushes them. So yeah, we long since realized, yeah, we're not going to find the oldest rocks in the solar system on Earth. Okay. But that's why when we went to the moon, we're like, this is our chance. This is our chance. So there are other methods. You saw one here. But even radiometric dating, we can use various other elements to use the same method. Say, well, let's try this element and this element and this element and this element. We can do that. We can detect in some extraordinarily sensitive means tiny bits of gas locked in rocks. We can examine the composition of those gases and say, well, those gases only existed in that proportion this long ago. I mentioned the sun. We have some very good now continuously improving theories of stellar formation. How do they form? At this mass, they take this long, and they burn like this, and they give off this much energy, and we go, yep, our sun fits right about there. Yeah, right about 4.6 billion years, yeah. So there are some other methods, if you want to do a little searching on that to corroborate the numbers from the rocks. Back there? Yeah.
Yeah, when Jupiter moved into like 1.5 years ago, where was the Earth? How was it affected by that?
Yeah. It's a good question. And to my knowledge, it was affected slightly, but not greatly. That is pretty close for a big Jupiter planet, right? And I don't have every last detail here to the very latest update, but that is a good question to go check and see what the thinking is there. We tend to look more for other effects that we can see, but now you got me thinking. Maybe it's time for me to go double check and see, yeah, what was the very latest there? To my knowledge, Earth moved modestly or slightly, but not dramatically enough. This was, of course, very early in the solar system's history. Life was certainly not even multicellular yet. It was single cell, so it's not going to really affect life that much. But we do know, obviously, life's been on Earth a long time. It was stable through that period. Okay. We're back there.
I've heard theories that Mercury formed further out from the sun that it currently occupies now. What do you know can tell us about that?
Once again, I don't have a lot of details. I have heard that as well. That's very possible. There's been some attempts to explain. You might know that Mercury has a proportionally oversized core. You know, Earth's interiors and the planets are divided into the core, kind of the mantle region, and stuff. Mercury's core is really big and massive. The real simplistic answer we generally tell students is, well, it's formed so close to the sun, it's going to lose much more of those lighter elements than other planets, say like Mars. In other words, Mercury's overall density is higher than Mars. It formed closer to the sun. That's pretty simplistic. There are some theories about how close it got to the sun, how it formed, where it formed. I don't have the very latest on those. But it only illustrates, again, that we are, number one, still learning, and number two, we're learning some interesting things. In other words, boy, our solar system may have had quite a history, as we described. Okay? Thought I saw one more hand. No? Yeah, Bill? Would you like to know?
So I wanted to ask about what appears to be a mini protoplanetary system, and that is the rings of Saturn.
Okay.
It certainly looks like a protoplanetary
Yeah.
model. We certainly see the flattening of the rings.
Yep.
Is there any evidence that a similar kind of accretion is happening within the rings that we suspect is consistent with the Nebular Theory?
Good question. Unlikely conclusion. What I mean by that, and just kidding, of course, but no, we don't really see a lot of accretion in Saturn's rings. So Saturn's rings look an awful lot like what I described. They're a very different beast. How'd Saturn ever get its rings? What we envision for Saturn is that Saturn, again, Jovian planet, very much like Jupiter. It's going to form a nice family of satellites. It's got one great big one, and it's got what we like to call the medium-sized moons. And you go, well, that's kind of odd. Why did you just have one big? What we think is very possible, we don't have proof of that, but we can first of all total up the mass in Saturn's rings, get a pretty good estimate, and it turns out to be similar to some of those medium-sized moons. When moons orbit a planet that closely, they feel a significantly stronger pull from the planet's gravity on the front of the moon as the back of the moon. This is very much like the effect here on Earth with tides. If you're familiar with how tides work, what's on the surface of the Earth? Water. And so as the moon comes around to a certain location overhead, it tends to pull the water more so towards it than the water on the other side of Earth, and we get a high tide. And then as the moon moves away, that tends to subside, and the high tide kind of follows the moon. Okay, my point in all that is if a medium-sized moon were, for various reasons, perhaps it's disturbed by its neighbors, one moon's pulling on another, and it gets itself a little too close to Saturn, boy, it's going to feel some serious gravity. The side closest to Saturn is going to be pulled more than the side farther, and we can easily show you that that will break a moon apart. Okay? That will break a moon apart. Shatter that moon, it will break into countless pieces, large and small, but those pieces will pretty much stay in the moon's orbit. Now they're going to spread out. Gravity's going to kind of shape them into a ring. It's going to gradually flatten that ring, as I described. And you might know this, you know, for many years we thought, oh yeah, Saturn's rings are really thin. Yeah, we used to think, well, they're, you know, like 100 miles. And then it was, well, now they're maybe only 10 miles. And then lately, you know, we send spacecraft out there, yeah, they're only a few hundred feet thick. So it's flat, and it's wide. So it's a different formation. Those particles, as you can imagine, the ones closer to Saturn are going to orbit Saturn faster. The ones farther are going to orbit slower. They're not going to want to stick together so much. So,
Do one more.
sure. One more question?
Right here.
was just gonna, so we're talking about the road limit,
The Roche limit, I meant to mention it.
and,
Mhm. The distance from Saturn.
I can't remember which one, but one of the moons of Mars apparently is, dangerously close to that situation. And we may get to see, a sort of a ring formation on Mars as a result of, that kind of, breakup.
It's certainly possible. To my knowledge, we're not expecting it anytime soon.
Oh, no.
But in the long term, yeah, that could play out, sure.
Like thousands of years or something?
I don't remember the exact number I saw somewhere, more like hundreds of thousands, but yeah, which is not that long.
Yeah, but
Yeah.
in terms of the whole universe.
Right.
Yeah.
So the point of all that is, ring systems are very interesting, but they're a little different than the formation of the solar system. The same physical laws apply, how it's going to flatten and it's going to spin, but if you might have watched that animation closely, you saw the inner regions spinning faster. They're closer to the sun than the farther, so it's harder for those particles to stick together. Pretty good questions. One more, last one?
The movement of the planets in the solar system, could that be the fact by Uranus? I mean, Neptune is at an angle, or it's tilted?
The movement of the planets?
Well, you know, you said the solar system, the planets are moving around.
Oh, shifting?
Would that
Yeah.
be the way?
So the fundamental answer to, so why is Uranus tipped over so much? Really, the most likely thing is a major impact tipped it over, okay? With all due respect to what you said earlier, to a gyroscope, but it tipped it over. There is ways to model that to get it to work. That seems to be the answer. So that, again, that would have been one of those larger planetesimals from way back early. All right, thanks again for having me tonight. Nice to see you all. Have a good night.
Thank you, Professor.
My pleasure.
You're a good partner of ours.
Thank you. My pleasure.
Amazing.
Give me this
A
back.
little bit of business for this evening. First off, I'll make sure to move to this group. Do you have any guests this evening, or new members? We always provide an opportunity to introduce yourself if that's the case, so I just want to put that out there. We're all about welcoming new members, and we're excited about new members that show up at our events, and so speaking of, okay. What else we got?
Can you put the slide up that shows the YouTube sites and I'll take a picture?
And I'm just gonna work top to
Sure
bottom.
can.
And